Hello, I'm Alessandro Tengattini. With Lucas Helfen, we are responsible of the neutron and X-ray tomograph of the ILL. So many of you will be familiar with radiography. So if you go to the hospital and you take a radiography of your hands, what you will see is a projection of your bones, typically across a plane. Now, in X-rays, what you see is essentially the bone because they are the denser part of your hand. That's because the opacity to X-rays is proportional to the atomic number of the elements and to their density. In neutrons, this contrast is a little bit different. And light elements such as hydrogen and lithium will be very, very highly visible, whereas metals, which are very opaque to X-rays, will be almost transparent to neutrons. What I'd like to stress is these two techniques are very highly complementary, which is a bit the idea underneath the neutron and X-ray tomograph, which we have developed here. Now, I mentioned a radiography. Radiography, as we said, is a projection along a plane. What is the difference then between a radiography and a tomography? The only difference is that in a tomography, we acquire a number of projections at different angles, and it is then possible to back project this information onto a 3D volume of the attenuation coefficients of the things inside. So it is possible not just to observe the outer surface, of course, but all the information inside your hand. In the case of the hand, the neutrons will, for example, see a lot of the hydrogen, so the blood vessels and so on will be really quite visible. Now, to the instruments. This is let's start with the neutron part. The neutrons are coming down this way. This is one of our several neutron detectors for different resolutions, and essentially these will the neutron will come down this way, will interact with the sample, and will be captured by this, which will transform the neutrons into visible light, which we can then capture with cameras. This is the rotation stage, which will allow you to take projections at different angles and then eventually to back projection to a 3D volume. This is for relatively large fields of view, up to about 20 centimeters down to resolutions about 20 microns, but we have other detectors that can push the resolution all the way down to about 3-4 microns. Now, to the X-rays. This is the X-ray generator. It's an X-ray microfocus source. It will project the X-rays against the sample. As you can see, they are at about 90 degrees from one another and will be captured by this detector. Now, it is possible in this instrument to capture the two of them at the same time. Why would that be interesting? Well, when there is a process ongoing, I'm thinking, for example, of a battery discharging or a flow or a compression of a porous medium or some such tests, it is important to have several images as the process develops. For example, one might want to quantify the displacement of the lithium within the battery, or of the water within a porous medium, or of the damaging of a metal under compression. Now, because the two techniques are so highly complementary, it is possible to study different aspects as the process goes on in a sort of a 5D, so 3D of the dimension plus time plus the different contrast that neutron and X-rays can provide. Let's take an example of a battery then. If we do a cycling, we will be able with the neutrons to see where the lithium goes as we charge and discharge the battery, and the X-rays will provide information about the intercalation within the electrodes and any damage that develops within the battery itself. So that's it. These are just some couple of very nice examples that can be done. Just to give you an order of magnitude, the time they can take for tomography goes from 1 second, which is our current record for a full 3D image, down to some hours if the resolution is closer to those 3 or 4 microns that I mentioned before, and in the X-rays is rather comparable.